Welcome everyone to the session on quantum 2 and separations. And the first talk of the session is about unclonable commitments and proofs by Vipul Golia, Julia Malavolta, and Justin Raisins. And Justin is going to give the talk.
Hey, I'm Justin. Thank you for the introduction. And I'll be talking about our work on clonable commitments and proofs. The starting point is just zero-knowledge proof. I'm sure that you are all familiar with this. But the idea is that we have a prover that wants to prove to some verifier the truth of some NP statement without revealing any additional information. And in particular, the verifier is not going to learn the witness. Right, so we can also consider a more complicated scenario where a prover sends their proof to the verifier, and then the verifier sends it on, maybe modified, to a third verifier. And this is the notion of a non-malleable proof, which was introduced a while ago. And now the key part to note here is that even though the verifier, this third verifier, might accept, the man in the middle that gives them their proof doesn't know the witness. So something intuitively is going wrong here. Now there are some tools to deal with this scenario, but the most basic thing that they can't deal with is the issue of just direct forwarding. So if the prover sends a message to the man in the middle, and the man in the middle just sends the message unmodified to the verifier, acting just as a communication channel, then the verifier is going to accept just by correctness. And there's nothing you can do to prevent this. But again, the man in the middle doesn't know the witness, so intuitively something's going wrong. And in this work, we're going to try and address this issue to try and control the flow of information. So the idea is perhaps we can use the fact that quantum mechanics does not allow the cloning of quantum states to do something about this. Right? You cannot send the same state to two different parties. So in this work, the question we ask is, can we construct proofs that cannot be cloned? And then an even more basic question of, can we construct commitments that cannot be cloned? So we're going to consider a scenario where a prover sends a commitment or proof to a man in the middle, and then the man in the middle sends their own commitment or proof to two different verifiers or receivers here. For this scenario, we give definitions for unclonable commitments and unclonable proofs, and then we give some constructions. The first scenario that we consider is the case where the protocol on the left side is the same as the protocol on the right side. This is very close to non-malleability, and it's a very natural setting. And in this case, we show how to build commitments from various assumptions with trade-offs. I won't have time today to get into all of them, but if you're interested, please take a look at the paper. And we also show that commitments are equivalent to public key quantum money. We can also consider a more demanding setting where the right sessions can use an arbitrary verification procedure. We just require that it is sound in some sense. And in this case, we show that we can construct unclonable commitments in the QROM, but proofs are just impossible in general. And intuitively, this is a much stronger statement about composability in this setting. For this talk, I'm just going to focus on the simpler setting of the same protocol. So let's start on the definitions. So to define unclonable commitments, we're going to start off with our standard commitment game where the challenger commits to one of two messages. Then we're going to deviate from the game a little bit, and the man in the middle is going to split the commitment into two pieces, com0 and com1. At this point, we'd like to argue, or we'd like to ensure that at least one of the two commitments is independent of the left. And so what we're going to do is, the third step of the game is an oracle is going to actually reveal what the committed messages were. So in the case where you give an invalid commitment, this is just going to be bought. But if there is an opening, then the oracle will reveal what message the commitment can be opened to. And then we consider two distinguishers that do not get to communicate, and they're trying to guess what the originally committed message is. And the guarantee that we want is the probability that they both are successful simultaneously is very close to 1/2. Let me go a little bit more into the intuition for this. If the man in the middle simply forwarded the commitment along one session, then this distinguisher is always going to guess the right bit. But on the other hand, we would like, in this case, for the other session to be completely independent. And so the probability that both of them are correct is going to be 1/2 because the other one is just randomly guessing. So that's the definition for commitments. It's also worth comparing commitments to a related notion of unclonable encryption. In an unclonable encryption, the adversary tries to split a ciphertext into two parts, and then later on, when it potentially steals the secret key for the encryption scheme, it's going to try and decrypt them. So this is similar, but it's also trying to do something slightly different than an unclonable commitment. Specifically, the adversary is trying to collect information for later use, right after it steals the key. On the other hand, in unclonable commitment, the adversary is trying to use the information right now, right? It's trying to give a commitment to a related message in both sessions. So there's a bit of a difference between the two notions. Now let's move on to proofs. We actually give two different definitions, but for the sake of time, I'm just going to go over one of them that is a little bit more natural, in my opinion. So the scenario that we're considering here is the prover will prove, using some witness, the truth of a statement to the man in the middle, and then the man in the middle will prove two statements to two different verifiers. The statements might be the same as the one on the left, they might be different. And what we would like is for there to exist a simulator that can simulate the adversary's view without the witness. But crucially, we also want this simulator to extract two potential witnesses from the right sessions. And the guarantee is at least one of the two witnesses should be valid if both right sessions accept. So intuitively, again, if the adversary just forwarded one session, this session doesn't have the witness, right? Because this is the left session is simulated. But we would like it to be the case that if it produces a second proof, it should know that witness in this case. In terms of constructing unclonable proofs, the starting point is to note that non-malleability is actually quite similar in the sense that we're trying to ensure that the right and left sessions are going to be independent. But remember that we cannot deal with forwarding. So the trick in that case in non-malleability is we identify each session with a tag. And we just guarantee that as long as the two sessions use different tags, then they're independent. So the key idea is that maybe we can make the tags unclonable, and then we can just use a non-malleable proof. So this gives us the idea of unclonable tag generation. So this is just a protocol where two parties, Alice and Bob, interact, and then at the end of the protocol, they output the same tag. And then you can use this for a non-malleable proof, potentially. For security, what we want is that if an adversary interacts with three different honest parties, then it cannot force all three honest parties to output the same tag. So if we had something like this, then if we think about that prior setting where we have the left session and the two right sessions, if we're guaranteed that the left session has a different tag than, say, the bottom right session, then that bottom right session is independent of the left session. And so we're guaranteed that at least one of the two sessions or one of the three sessions is different. So this is actually pretty easy to construct using public key quantum money. In this, we'll consider an offline phase where a bank just sends some quantum money states to each of two parties. And I'm going to highlight one of these quantum money states that we're going to use up for the tag generation. To generate a tag, Alice just picks her quantum money state and sends it to Bob. And then she outputs the serial number. And Bob, before outputting anything, is going to check that the serial number matches. If so, he just outputs the same serial number. Now, intuitively, because of the security properties of quantum money, the adversary cannot create two banknotes with the same serial number, and so at least one of the two will reject. In terms of commitments, we can actually get a construction without public key quantum money. And the key observation is we don't need the tag to be immediately checkable. In fact, there are two phases here, so we can kind of sneak in some interaction, where there's a commitment phase and then an opening phase. And so we can generate the tag and use it without actually checking it in the first phase. And so we don't need public verifiability in this phase. Then, in the second phase, we can reveal the secret information that allows the tag to be generated or checked. Yeah. So that brings me to the end. Thank you for listening.
Any questions for Justin? Then maybe I have a quick question. You said that in the strong unclonable model, proofs are impossible. Can you give a hint?
Yeah.
What this is related to?
It's probably easiest to describe with non-interactive proofs. But the idea there is you can, because you're allowed to do a slightly different protocol, you can add additional messages. And so now you can send the proof to one party, they can verify it, and then they send it back. And now you can send it to the second party. For the full version, you have to do some MPC tricks.
All right. Thanks a lot. So let's thank Justin again.